Good morning. Today I will cover one more algorithm, which is Floyd and Warshall algorithm. This algorithm is all pairs shortest path algorithm, and we will be solving the problem. I will explain the problem, and we will be solving the problem using a dynamic programming approach. Now, the problem. Let's understand the problem. What is the meaning of all pairs shortest path? The problem at hand is to find the shortest path from every pair of vertices. That means, let's say we start from 1. What is the shortest path from 1 to 2, from 1 to 3, 1 to 4? Let's say we start from 2. What is the shortest path from 2 to 1, 2 to 3, 2 to 4? And in this example, since only 4 nodes are there, and what is the shortest path from 3 to 1, 3 to 2, 3 to 4, 4 to 1, 4 to 2, and 4 to 3. So meaning by, we have to find the shortest path from all the pairs of vertices. All right. Now, Dijkstra's algorithm is also very similar kind of algorithm. Dijkstra's algorithm will find shortest path. It will also find the shortest path, but it will find the shortest path from single source. That means, let's say I fix my starting node as 1, so I will find the shortest path of vertex 1 from all the vertices. But in the all pairs shortest path Floyd and Warshall algorithm, we will find out the shortest path of all the pairs. Now, in the Dijkstra's algorithm, what is the complexity of the algorithm? It is O(n) square. But if we have to use the same technique as Dijkstra's algorithm, and we have to find all pairs shortest path, then since n vertices are there, like one source takes O(n) square of time, and how many sources are there? How many source vertices can be there? There can be 4 vertices. So n square into n will be O(n) cube. That's the all pairs shortest path can be solved using, because if you remember, I solved the Dijkstra's algorithm using greedy approach. Now, if I use the greedy approach, so that means I will be able to solve all pairs shortest path algorithm in O(n) cube complexity. But we will apply here. We will not use the dynamic programming approach. We will not use the greedy approach here. Rather, we will use the dynamic programming approach. And it says that the general definition of dynamic program, it says that we must consider a substructure and also overlapping. I have already explained the meaning of these things. Now let's look at the solution of this problem. I will use the same problem and I will solve this problem so that you understand what is the meaning of this all pairs shortest path algorithm. And this will be one more example of dynamic program. So let's see how it can be solved. Now, so what we will do is actually we will find out. Let's say we want to find out the shortest path from 1 to 2, but the approach that will be used is, okay, this is the path from 1 to 2. Is there any other shortest path if we go to 2 but go via 3 or go via 4? So that means whether a shortest path exists for going from 1 to 2 via 3 or via 4. So it is based on this. Basically, this is the strategy. So we will consider that if there is a path from 1 to 2, right? And if there can be other shortest path, if we go from 1 to 3 and then to 2, or 1 to 4 and then to 2, and we will calculate the whole problem using this strategy. So the example that I have taken is the same example. All right, this is a four vertices example, and this is the cost adjacency matrix of this graph. Now, what is this superscript? There is a superscript actually A0. I will explain. This is the original matrix. What is the meaning here? Because we will solve this problem using the method of matrices. So this is the AO or A0 if you call it. So this is the original matrix. Now, step one is I will have to start by taking vertex 1 as the middle vertex. So we have to take, because going from 1 to 2, I am going from 1 to 3. That means there will be a middle vertex also in this example. So we will start this algorithm by considering 1 as the middle vertex, right? And let's see how this original cost adjacency matrix can be modified. All right. Now, if I am taking 1 as my middle vertex, then what? Right. So 1 will be my middle vertex. So the first point is that there is no self loop for this one. So this diagonal elements will remain 0 as these were in the original matrix. The diagonal elements will remain 0. How we are representing the cost adjacency matrix? Since there is no self loop, so self loops are the diagonal elements and they are being represented by zeros. And if there is no edge, for example, from 1 to 3, so 1 to 3 there is no edge, there is no direct edge, so it will be represented by infinity. So that's the representation of the matrix. And from 1 to 2, the cost is 3. So these are the costs. So particularly I am explaining about zeros. These zeros are basically for self loops. Infinity is basically for if there is no edge from one vertex to the other. We will have to modify this matrix once we have taken once we have taken the vertex 1 as the middle vertex. All right. How to modify this matrix? That's the that is to be understood basically. All right. So since there are, if 1 is the middle vertex, then corresponding to 1, the row and the column will remain the same. What is the row here? Corresponding to 1, vertex 1, 0, 3, infinity 7. So 0, 3, infinity 7 remains the same. What is there in the column? 0, 8, 5, 2, 0, 8, 5, 2. So the column also remains same. The diagonal elements also remain the same because there is no self loop. Rest of the elements we have to modify. So let's see. So where should we start from? Because the first row is the same as the original adjacency matrix. This 2, 1 element is also the same because it falls in the column 1 corresponding to vertex 1. So now we will have to modify this element. And this element is 2, this is also 0. This is the diagonal element. This is not to be modified. This element, which is 2 here, that means 2, 3 element has to be modified. So that's how I am modifying the 2, 3 element in the matrix. So I will take the 2, 3 element from the original matrix. What is 2, 3? It is 2. So I put 2 here. I take the first vertex from here, which is 2, and I use 1 as the middle vertex. So that means my first the element will be here 2, 1 because 1 is the middle vertex. And plus, since 1 is the middle vertex between 2 and 3, the first element will be 2, 1. The second element will be 1, 3. These will be added. So that means this element. What is this element? A2, 3. A2, 3 is 2. I wrote here. And A2, 1. What is A2, 1? It is 8. So I wrote 8 here. Plus, what is A of 1, 3? 1, 3 is infinity. So 8 plus 3. Using 1 as the middle element. What is 8 plus 3? 8 plus infinity. It is infinity. What is this on the left side? It is 2. So that means 2 is less than infinity. So I will keep 2 here. Whichever element will be less by this method, I will keep that element. All right. So now let's look at the next element. Next element is A2 comma 4. What is A2 comma 4 in the original matrix? In the original matrix, it is infinity. So I put infinity here. So taking 1 as the middle element. What is 2 comma 1? 2 comma 1 is 8. And what should be the second element? 1 comma 4, because I have to place 1 here. 2 comma 1 and 1 comma 4. And 1 comma 4. 1 comma 4 is 7. Right? So I place 7 here. What is 8 plus 7? 8 plus 7 is 15. What is infinite? This side is infinity because A2 comma 4 is infinity, which is greater than 15. So that means 15 is less than infinity. So therefore, what will be the A in this matrix? What is this matrix? This matrix is the modified matrix when vertex 1 is taken as the middle element. So what will be the element 2 comma 4? It will be 15 because 15 is less than infinity. So let's look at one more element. Let's look at this A3 comma 2. So what is A3 comma 2 here in the original matrix? 3 comma 2, again it is infinity. So I put infinity here. So it has to be 3 comma 1 and 1 comma 2. 3 comma 1 and 1 comma 2. What is 3 comma 1? 5. What is 1 comma 2? 1 comma 2 is 3. So 5 plus 3, it is 8. 7 is less than 8. So therefore, 3 comma 2. No, I'm sorry. It is yes, it is infinity. A3 comma 2 is infinity. A3 comma 1 is 5. A1 comma 2 is 3. 5 plus 3 is 8. Infinity is greater than 8. So this element will be replaced. In the original matrix, if you see, it was infinity, but corresponding to the 1 as the intermediate element. So therefore, this element will be 8 here. I hope the logic will be clear. And this way, using this method, we will be calculating all the elements of the matrix corresponding to 1 as the middle vertex. All right. Now because we have to calculate all pairs the shortest path. This matrix we have modified corresponding to 1 as the middle vertex. Similarly, we will have to go for 2 as the middle vertex. So there will be another matrix, 3 as the middle vertex, another matrix, 4 as the middle vertex, another matrix. In all, there will be 4 matrices, newly generated 4 matrices corresponding to 2, 3, 4, 1, 2, 3, 4 as the intermediate or middle vertices. All right. So let's further look at the problem. Let's calculate some elements use of this A superscript 2, meaning by we are using 2 as the middle element. But when we were calculating for 1 as the middle element, we use the original matrix A0. But for calculating A2, where vertex 2 is being used as the middle element, we will use A1 matrix. All right. So since 2 is the middle element here, 2 is the middle element here, corresponding to 2. Since 2 is the middle element here, corresponding to 2, the second row and second column will remain as it is. So what is the second row here? 80215. 80215 remains the same. What is the second column? Second column here is 3085. The second column is 3085. All right. Now let's calculate some of the elements. The first element will be, let's say what we are trying to calculate. Let's look at 1, 3. And of course, the diagonal elements will also remain the same because there is no self loop. So what we have done for calculating A2 is that the second row and the second column will remain the same as A1. All right. So 0 is there, which is the diagonal element, it will remain 0. This element we have fixed because it belongs to the second column. Now we have to calculate for 1, 3. So we have to calculate for we have to calculate for 1, 3. That means this element is there na? In the second matrix, in the matrix for A2, we have to calculate for 1, 3. How to calculate it? What is 1, 3 in this matrix? 1, 3 here is infinity, so I put infinity here. So I'm using 2 as the middle vertex. So 1, 2 plus 2, 3. What is 1, 2 here? 1, 2 is 3. So I place 3 here. 2, 3. 2, 3 is 2 here. So I place 2 here, which is 5. So the addition of these two elements is 5. This infinity is greater than 5. So that means 5 is less than infinity. So I will, what is my A 1, 3 element in this matrix? It is 5. So that's why I have placed 5. Right, the same procedure as we used for when vertex 1 was taken as the middle vertex. Now let's look at one more element. We will now calculate in this matrix the 1, 4 element. So what is 1, 4? What is 1, 4 here? It is 7. So that means 1, 2 and 2, 4 are to be added. 1, 2 and 2, 4. 1, 2 is 3. 2, 4. 2, 4 is 15. So 15 plus 3 is 18. 7 is less than 18. So here the 7 will hold because 18 is greater than 7. So we have to place the element which is smaller than the addition of these two. All right. So I will not calculate the rest of the elements. The procedure remains the same. So this is the element. This is the matrix obtained. This is the matrix A2, meaning by this matrix is for using when we are using 1 as the middle vertex. This matrix is when we are using vertex 2 as the middle vertex, and we had one original matrix. Similarly, when we will use 3 as the middle vertex, we will obtain this matrix. Let's calculate one of the elements. So it is A3. A3 means the third row and third column will remain as it is. And which matrix we have to use? Now we have to use A2. For calculating A2, we used A1. For calculating A1, we used the original cost adjacency matrix. For calculating A2, we used A1. For calculating A3, we will use now A2. Now, third row. What is third row? It is 5801. So it is placed as it is. What is third column? 5207. 5207 is placed as it is. Right? And the diagonal elements are all 0 because there is no self loop. So what element we will have to calculate? We will have to calculate start from 1, 2. So what is 1, 2 in this matrix? It is 3. So I place 3 here. So 1, what will be the addition? 1, 3 plus 2, plus 3, 2. Sorry, because 3 is the middle element. So what is 1, 3 here in this matrix? 1, 3 is 5. So 5 comes here. What is 3, 2? 3, 2 is 8. So 8 comes here. It is 3. So that means 3 is smaller than this 13. So therefore, this 3 holds here at this point. Right? So I mean, you have to use the same procedure to create 4 matrices from the original matrix. What are those 4 matrices? Those are, the first matrix is the matrix corresponding to when we are using vertex 1 as the middle element. The second will be for when we are using vertex 2 as the middle element. The third matrix is when we are using vertex 3 as the middle element. And fourth one is when we are using vertex 4 as the middle element. In all, you will have 4 matrices available. All right. So basically, these will give you, when you are using 1 as the middle element, what is the shortest path from 1 to 3? What is the shortest path from 1 to 3? Infinity. So there is no way to read. Actually, these are giving the shortest path. This algorithm, the procedure, what we have done till now, is giving us the all pairs shortest path, right? And this is the algorithm basically. We'll have to actually, I have not directly written the equation. Rather, I have shown you how to actually calculate the values. But let us derive, because we have to write a program for this algorithm, let us derive from this procedure only. Sorry. Let us derive an equation of the generation of the matrices. Let's look at the general equation. The general formula is framed like this. What is this AK? AK is basically, I will take this example, A2, and then create A2 here, K is 2 here, right? Okay, so K is, I comma J are the indices for the rows and columns. K is the, which vertex we are taking as the middle vertex. So K is the middle vertex, right? So A, whatever is the middle vertex, and all the elements in the matrix. So what is this equal to? All the elements will be equal to minimum of what? If you see here, we were taking this A1, A of 1, 1, 3, A of 1, 1, 2 plus A of 1, 2, 3. For calculating A of 2, when 2 is middle vertex, what we were taking, how we were calculating this value? We were calculating this value using, by looking at this value. The minimum, we were taking minimum of these two values, the addition of these two and this value, we were taking the minimum value and we were placing in at this point. So that's what is the equation. K is the middle vertex. I, comma J are the indices for the elements. We are taking minimum element of what? 1, we are seeing this element, K minus A of K minus 1, I comma J, comma, and the addition of these two, because K is the middle element. I have written the same formula here. This is the same formula. The same formula. This is the I comma J element, comma, we are taking minimum of A K minus 1 I comma J, comma, A K minus 1, the previous matrix, I comma K, where, because when it is 1 comma 3, then I am taking 1 comma 2 and 2 comma 3. 2 is the middle element here because I am calculating the elements for the middle vertex. So that is why A K minus 1 I comma J, comma, A of K minus 1 of what? I comma K plus A K minus 1 of K comma J. 1 comma 2, 2 comma 3. Right? So this is the general formula for calculating the elements of the new matrix, right? Taking K as the middle element. I comma J will give you the rows. K is actually looping for the middle element. Now, every time, it is time here, every time I was generating the matrices, and how many matrices I have generated? I have generated 4 matrices. For generating a matrix, right, I should generate each and every term. How many total terms are there? It is n comma n, because n are the number of vertices, right? So it is n square elements I will have to generate. So how to write a program for this, for a matrix? you need to write two for loops. First for loop is I comma 1 will be for row, going from 1 to 4 in this example, or 1 to n, because it's a square matrix. So, and the second loop is for columns. So two loops are for generating the elements of one matrix, and this is the equation that I have explained just now. This is A of I comma j is equal to minimum of I comma j, minimum of A I comma j, comma the addition of these two, where k is the middle element, right? So these are the, so this will give me the matrices. What is this third for loop? This third for loop is taking k as the index. When k is equal to 1, that means when we have taken 1 as the middle element, so the matrix will be generated. When we are taking k equal to 2 for the next iteration, the matrix will be generated for when we have taken 2 as the middle element, then 3 as the middle element, and then 4 as the middle element. So 4 matrices in our example will be generated by the first for loop. So this is the program for, this is the general pseudo code for writing the program for this Floyd Warshall algorithm. What is this algorithm giving? This algorithm is giving us the shortest path from every pair of vertices. This is different from Dijkstra's algorithm. This is using the dynamic programming approach, whereas in the Dijkstra's algorithm we use the greedy approach, and what is the Dijkstra's algorithm? It is only calculating the shortest path from one single source. But this algorithm is giving us the shortest path from all the vertices, from all the pairs, considering all the pairs. I hope you have understood the algorithm, right? One more topic I have to discuss here. Only one slide is left. Today will be a shorter lecture. Only one slide is left. This slide is actually a compact list representation of a graph. This is very important also. Now, what we have done till now? Till now, I have explained you, for example, here, this matrix was used to represent this graph. What this matrix is known as the cost adjacency matrix. The cost adjacency matrix is one way to represent the graph. The second method is adjacency list. If you remember, we were using it as a linked list. There is a matrix. So I have already covered that because I don't have the slide. I don't want to, only verbally explain the things here, which will unnecessarily confuse. So there are two methods. One is the cost adjacency matrix like this. The second method is the cost adjacency list, which I have already explained. Now, third method of representing a graph is compact list. So let's look at what is this way of representing the graph. I have taken this example of graph with 5 vertices. This is a graph. How many vertices are there? 5 vertices are there. How many edges are there? 7 edges are there. We need to represent a graph using compact list. We need a single dimensional array. And what should be the size of the array? Size of the array should be number of vertices plus twice the number of edges. Why? Because we are considering both the options. Edge from 1 to 2, 2 to 1, right? So both options are there. So it is number of vertices plus twice the number of edges plus 1. This is the formula for which will give me the number of elements. We'll see the entries, how to make the entries. So this will give me the array size, right? So in this example, how many vertices are there? 5 vertices are there. How many edges are there? So 5 plus 2 into 7, 5 plus 14 is 19, plus 1 is 20. One more is added because the indices will start from 0. All right, so that is why it is up the array that I have shown here is up to 20 only. This is redundant. 21, 22, these are not to be considered. So the array is from 0 to 20. So that means how many spaces we require? We require 20 plus 1, 21 spaces we require, right? Now how to make the entries? The first entry, we will not use this this space. The first space we will not use in the compact list. Now 1, 2, 3, 4, 5, because how many vertices are there? 5 vertices are there. The array index 1, 2, 3, 4, 5, these are for the vertices. Okay, we will see what is to be filled here, but these are for vertices. The sixth space will also not be used. I will explain how this entry has come, but we will not, for the present time, we will not consider this sixth also. Now let's start from 7. And let's consider vertex 1. What are the vertices connected to 1? 2, 3, 4. 5 is not connected. So that is why it is 2, 3, 4. What is this? And these entries 2, 3, 4 entries are adjacent vertices of vertex 1. All right. And from where these edges are starting for corresponding to vertex 1, it is starting from 7. So that is why at this point this 7 will come, which will directly give me the edges which are connected to vertex 1 are starting from 7th entry. 2, 3, 4 will be for vertex 1. Let's look at 10 and 11. Let's look at vertex 2. Vertex 2 is connected to 1 and 3. So 7, 8, 9 are for 1. 10 and 11, we place 1 and 3 here because with vertex 2, 1 and 3 are connected. And we will place at the next point at this entry number 2, 10. What is 10? 10 is the start of the adjacent vertices for vertex 2. And this is for vertex 3. Vertex 3 are connected to 1, 2, 4, 5, starting from 12. So we place 12 here. For vertex 4 is connected to 1, 2, 3, 1, 3, 5. 1, 3, 5 is placed here. From where corresponding to entries, corresponding to vertex 4 entries are there? From 16. So we place 16 here. Then for vertex 5 is connected to 4 and 3. So this 3 and 4 are connected. The entries are starting from 19. So it is 19 here. And it is going up to where? 19 and 20. What we will place here? 21. Outside the size of the array. So that means this is the final point. Outside the size of the array will come at the 6th position. All right. So this is the method of representing. If you don't draw this graph, and if I give you the compact list only, right? Actually, it is explaining the graph. You should be able to, if I tell you that this is, you can see from the array size also, and you can get everything about the graph from this compact list only. In this array, one-dimensional array, there is no mention of these costs corresponding to the edges. Now, if you want to put the costs also, then you will have to take another array of the same size, and corresponding to vertices, you can put the cost also. For example, these entries are for vertex 1. Going from 1 to 2, what is the cost? Going from 1 to 2, the cost is 9. So at 7th position, 9 will come, right? So you can have the cost also by having one more array of the same size. Now, what is the space consumed? Space consumed is the same. The same as this formula. V plus 2 E plus 1. So this is basically linear. The space consumption is, the complexity is ON. For weights, you take another array of the same size and correspondingly you can place the cost. This is the end of my lecture today, right? Next time I will cover one more algorithm. Actually, most of the algorithms are covered in your whatever is there in your syllabus, but I will try to cover one or two more because we have time left for the class. Okay.
So can you send the syllabus?
I will send you the syllabus. I'm sorry, you asked last time also. I will send the syllabus right now only. I will send the file also, video file and the syllabus. Okay.
Fine, sir. Okay.
Thank you so much. Thank you. Please remain safe, right? Stay at home. Thank you.
Chennavira.